Welcome, viewers. Today, we're embarking on an electrifying journey through time. We'll explore the fascinating history of electricity, a force that has revolutionized our world in ways our ancestors could never have imagined. From the first curious observations of static electricity in ancient times to the complex power grids that fuel our modern world, electricity has been a driving force of human progress and innovation. But what exactly is electricity? At its most basic, electricity is the flow of electric charge. It's a fundamental part of nature, present in lightning storms, in the synapses of our brains, and even in the atoms that make up everything around us. Yet, harnessing this power for human use has been a long and fascinating journey. Electricity is unique among energy sources. Unlike coal, oil, or natural gas, electricity is a secondary energy source, often called an energy carrier. This means that electricity is generated from the conversion of other sources of energy, such as coal, nuclear, or solar energy. This versatility is part of what makes electricity so valuable. It can be generated from a wide variety of primary energy sources and used for an even wider variety of applications. The story of electricity is not just a tale of scientific discovery. It's a story of human ingenuity, of trial and error, of competing visions and technologies. It's a story that has shaped our modern world in profound ways, influencing everything from industrial production and urban development to domestic life and personal communication. So, are you ready to be shocked by the story of electricity? Let's plug into history and switch on our time machine. Our story begins over 2,500 years ago in ancient Greece. Around 600 BCE, the philosopher Thales of Miletus noticed that when amber was rubbed with fur, it could attract light objects like feathers. This was the first recorded observation of static electricity. Thales's observation was significant not just for what he saw, but for how he interpreted it. Unlike many of his contemporaries who might have attributed such phenomena to the gods, Thales sought a natural explanation. This approach laid the groundwork for scientific inquiry into electrical phenomena. The Greeks weren't the only ones to notice electrical effects. In ancient Egypt, texts refer to thunderers of the sky and guardians of the Nile, electric fish that could deliver a shock. These electric catfish were even depicted in hieroglyphics. Some historians believe that the ancient Egyptians may have used the shocks from electric fish medicinally to treat pain or other ailments. Meanwhile, in ancient China, texts from around 2,000 years ago describe lodestones, naturally magnetized pieces of the mineral magnetite. The Chinese discovered that when a lodestone was suspended so it could turn freely, it would always point in the same direction. This led to the invention of the compass, which revolutionized navigation. In the ancient world, we also find the first descriptions of one of nature's most spectacular electrical displays: lightning. Many cultures had myths explaining lightning as the weapon of a sky god. Zeus for the Greeks, Thor for the Norse, and Indra in Hindu mythology. However, some ancient thinkers had more scientific ideas. The Roman philosopher Lucretius speculated that lightning was made of tiny particles that flowed through the clouds, an idea not too far from the truth. Despite these observations and speculations, for centuries, electricity remained largely a curiosity, a strange force that could make hair stand on end or create sparks, but with no practical applications. People were aware of its effects, but had no understanding of its nature or how to control it. As we enter the Middle Ages, progress in understanding electricity and magnetism slowed, but didn't entirely stop. In the 11th century, the Persian physicist Ibn al-Haytham, also known as Alhazen, wrote extensively on optics and the nature of light. While not directly related to electricity, his emphasis on experimentation and mathematical description of natural phenomena would influence later scientists studying electricity. The 13th century saw a resurgence of interest in natural phenomena in Europe. The English monk and scholar Roger Bacon, inspired by the work of Islamic scientists, advocated for empirical study of nature. He wrote about magnets and static electricity, though like his predecessors he couldn't explain the forces at work. Around the same time, another European scholar, Petrus Peregrinus, wrote what is considered the first treatise on magnetism. His work, Epistola de Magnete, Letter on the Magnet, written in 1269, described many properties of magnets, including the fact that every magnet has two poles, and that like poles repel while opposite poles attract. However, during this period, many electrical phenomena were still attributed to supernatural causes. St. Elmo's fire, a weather phenomenon in which luminous plasma is created by a coronal discharge from a sharp or pointed object in a strong electric field, was often seen by sailors. They interpreted it as a good omen and associated it with their patron saint, St. Erasmus of Formia, also called St. Elmo. As we enter the 17th and 18th centuries, the Age of Enlightenment brings a new spirit of scientific inquiry. This era sees the first serious attempts to understand and control electricity. In 1600, English physician William Gilbert coined the term electric in his work, de magnet, from the Greek word for amber, electron. Gilbert was the first to make the crucial distinction between magnetism and static electricity. This book was groundbreaking not just for its content, but for its method. Gilbert conducted numerous experiments and was one of the first to insist that scientific theories should be based on experimental evidence rather than pure reasoning. The 18th century brought a flurry of electrical experiments. In 1729, Stephen Gray discovered electrical conduction, showing that electricity could be transferred from one object to another. He also found that some materials conducted electricity better than others, laying the groundwork for our understanding of conductors and insulators. In 1733, French chemist Charles-François de Cisternay-Dufay discovered that electricity comes in two forms, which he called vitreous and resinous. We now know these as positive and negative charges. This was a key step in understanding the nature of electricity. But perhaps the most famous experiment of this era came in 1752, when Benjamin Franklin flew a kite during a thunderstorm. Franklin's dangerous experiment proved that lightning was a form of electricity, unifying our understanding of natural and artificial electrical phenomena. Franklin made several other important contributions to electrical science. He introduced the terms positive and negative to describe electric charge, replacing Dufay's vitreous and resinous. He also developed the concept of conservation of charge, noting that when one object was charged positively, another was always charged negatively by the same amount. Franklin's most practical contribution was the invention of the lightning rod. By showing that pointed metal rods could protect buildings from lightning strikes, Franklin provided the first practical application of electrical science, saving countless lives and properties. Another key figure of this time was Italian physicist Alessandro Volta. In 1800, Volta created the voltaic pile, the first electrical battery. This device could produce a steady electric current, a huge improvement over previous static electricity generators. The voltaic pile provided the first reliable source of electrical current, crucial for further experimentation and development. The 19th century saw an explosion of electrical discoveries and inventions that would change the world forever. This era is marked by the transition from electricity as a subject of scientific curiosity to a powerful technology with practical applications. In 1820, Danish scientist Hans Christian Ørsted discovered that electric current produces a magnetic field. This crucial finding linked the previously separate phenomena of electricity and magnetism. Building on Ørsted's work, British scientist Michael Faraday made a series of groundbreaking discoveries. In 1831, he found that a changing magnetic field can induce an electric current in a nearby wire, the principle of electromagnetic induction. This discovery is the foundation of modern electric motors and generators. Faraday also introduced several important concepts to electrical science. He coined terms we still use today, like electrode, cathode, and ion. He also developed the concept of electric and magnetic fields, visualizing them as lines of force in space. Meanwhile, in 1827, German physicist Georg Ohm published The Galvanic Circuit Investigated Mathematically, establishing Ohm's law. This law, which describes the relationship between voltage, current and resistance, is fundamental to electrical engineering. Later in the century, James Clerk Maxwell would unify electricity and magnetism into a single theory of electromagnetism. Maxwell's equations, published in 1865, described how electric and magnetic fields interact and propagate through space as waves. These theoretical advances paved the way for practical applications. In 1837, Samuel Morse invented the electrical telegraph, revolutionizing long-distance communication. Morse's invention was not just a technological marvel, it changed society by allowing near-instantaneous communication over vast distances. But perhaps the most iconic invention of this era came in 1879, when Thomas Edison successfully demonstrated his incandescent light bulb. While not the first electric light, Edison's was the first practical and long-lasting one. Edison's genius lay not just in inventing the light bulb, but in developing an entire system for electrical lighting. Edison went on to develop the first electrical distribution system, lighting up parts of New York City in 1882. His Pearl Street station was the world's first central power plant, using large steam engines to drive electric generators. However, Edison's direct current, or DC system, had limitations. It couldn't transmit electricity over long distances without significant power loss. Enter Nikola Tesla, a brilliant inventor who had once worked for Edison. Tesla championed alternating current, or AC, which could be easily transformed to higher or lower voltages, allowing for long-distance transmission. Tesla's AC system was backed by industrialist George Westinghouse, leading to a fierce competition known as the War of Currents. This battle between AC and DC systems would shape the future of electricity distribution. Eventually, Tesla and Westinghouse's AC system won out due to its superior long-distance transmission capabilities. Early 20th century electrification transforms society. The dawn of the 20th century saw electricity move from a novelty to a necessity, transforming every aspect of society. This period is marked by the rapid expansion of electrical infrastructure and the proliferation of electrical devices in both industry and the home. In 1895, the Adams Power Plant at Niagara Falls opened, marking the beginning of large-scale electricity generation. This hydroelectric plant, which used Tesla's AC system, not only powered nearby Buffalo, New York, but demonstrated the feasibility of transmitting electricity over long distances. Electricity began to transform every aspect of life. In homes, electric lighting replaced gas lamps, dramatically reducing the risk of fire and improving indoor air quality. A host of new appliances appeared, from electric irons and vacuum cleaners to radios and refrigerators. These devices promised to ease the burden of household chores and improve quality of life. The impact on domestic life was profound. Electric lighting extended the day, allowing for more productive and leisure hours. Refrigerators revolutionized food storage and nutrition. Electric washing machines and vacuum cleaners reduced the time and effort required for household chores, particularly impacting women's daily lives. In industry, the impact was even more dramatic. Electric motors began to replace steam engines, allowing for more flexible factory layouts and increased productivity. The assembly line, pioneered by Henry Ford in 1913, was made possible by electricity. This new form of manufacturing dramatically reduced the cost of goods, making many products accessible to average consumers for the first time. Electricity also revolutionized communication. The telephone, invented by Alexander Graham Bell in 1876, became widespread in the early 20th century. By 1900, there were nearly 600,000 telephones in the United States. By 1930, there were over 15 million. The 1920s saw the birth of another revolutionary communication technology, radio broadcasting. The first commercial radio station, KDKA in Pittsburgh, began broadcasting in 1920. By the end of the decade, radio had become a major source of news and entertainment, creating shared national experiences and reshaping popular culture. However, electrification was not uniform. In the United States, while 85% of urban dwellers had electricity by 1930, only 10% of rural homes were electrified. This disparity led to government initiatives like the Rural Electrification Act of 1936, aiming to bring electricity to all Americans. Mid-20th century, the electrical age matures. The mid-20th century saw electricity become ubiquitous in developed countries. Power grids expanded and became more interconnected, improving reliability and efficiency. This period also saw significant advancements in electronics, setting the stage for the digital revolution. World War II had a profound impact on electrical and electronic technology. The war effort spurred advancements in radar, radio communication, and early computing. The first electronic digital computer, ENIAC, Electronic Numerical Integrator and Computer, was completed in 1945. While it filled a large room and consumed massive amounts of electricity, it paved the way for the computer revolution that would follow. The post-war economic boom saw a proliferation of electrical and electronic consumer goods. Television, which had been experimental before the war, became widespread in the 1950s. By 1960, nearly 90% of American households had a TV set. Television changed entertainment, advertising, and political communication, becoming a central part of modern culture. This period also saw advancements in power generation technology. In 1951, a small experimental breeder reactor in Idaho became the first nuclear reactor to produce usable electricity. The first full-scale nuclear power plant began operating in Obninsk, USSR in 1954. Nuclear power promised abundant, cheap electricity, though its adoption would later become controversial due to safety and environmental concerns. The space race between the United States and the Soviet Union drove further advancements in electronics. The need for small, lightweight electronic components for spacecraft led to the development of integrated circuits. The first integrated circuit was demonstrated by Jack Kilby at Texas Instruments in 1958, laying the groundwork for the microelectronics revolution. This period also saw the beginnings of renewable electricity generation beyond hydropower. The first practical solar cell was developed by Bell Labs in 1954, with an efficiency of about 6%. While too expensive for widespread use at the time, it was used in spacecraft and set the stage for future developments in solar energy. Wind power, which had been used for mechanical power for centuries, began to be seriously explored for electricity generation in the 1970s in response to the oil crises. Early wind farms were built in the United States and Denmark, marking the beginning of modern wind power. Late 20th century to present the digital revolution and beyond. The late 20th century saw electricity and electronics become inseparable from daily life. The invention of the microprocessor in 1971 by Intel marked the beginning of the personal computer revolution. The first personal computers appeared in the mid-1970s, and by the 1980s they were becoming common in homes and offices. The rise of the internet in the 1990s created an always-on, interconnected world with an insatiable appetite for electricity. The first popular web browser, Mosaic, was released in 1993, making the World Wide Web accessible to non-technical users. As internet use exploded, so did the need for data centers, massive facilities filled with energy-hungry servers. The mobile revolution, kicked off by the introduction of the iPhone in 2007, further increased our reliance on electricity. Smartphones and tablets created a demand for constant connectivity and frequent battery charging. The Internet of Things, everyday objects with network connectivity, further expanded electricity use. Concerns about climate change brought renewed focus on how we generate electricity. Renewable sources like wind and solar saw rapid growth, aided by technological improvements and falling costs. In 2019, renewables accounted for 72% of all new power capacity added globally. Solar power, in particular, has seen dramatic improvements. From the 6% efficient solar cells of the 1950s, modern photovoltaic cells can exceed 20% efficiency, with some experimental cells reaching over 40%. The cost of solar panels has plummeted, making solar power competitive with fossil fuels in many areas. Wind power has also advanced significantly. Modern wind turbines can be over 200 meters tall, with a single turbine capable of powering hundreds of homes. Offshore wind farms, first installed in Denmark in 1991, have become increasingly common, taking advantage of strong and consistent ocean winds. The way we distribute and use electricity is also changing. Smart grids, which use digital technology to monitor and manage the transport of electricity, are improving efficiency and reliability. Smart meters in homes and businesses allow for more precise monitoring and control of electricity use. Energy storage technologies are advancing rapidly, crucial for managing the intermittent nature of many renewable energy sources. While pumped hydro storage has been used for decades, newer technologies like lithium-ion batteries are becoming increasingly important. Tesla's Powerwall, introduced in 2015, brought battery storage to the home market. Electric vehicles, or EVs, are reshaping transportation and electricity demand. From early models like the GM EV1 in the 1990s to modern vehicles from Tesla, Nissan and others, EVs are gaining market share. This shift promises to reduce oil dependence and could significantly impact electricity demand and grid management. Looking to the future, several technologies hold promise for revolutionizing electricity generation. Nuclear fusion, which promises abundant clean energy, has seen recent breakthroughs. While still experimental, projects like ITER aim to demonstrate the feasibility of fusion power. Advanced solar cells, using new materials like perovskites, could dramatically increase efficiency and reduce costs. Space-based solar power, collecting solar energy in orbit and beaming it to Earth, is being seriously studied by several countries. Small modular nuclear reactors could provide scalable, low-carbon baseload power with enhanced safety features. These reactors, which can be manufactured in factories and transported to sites, promise to make nuclear power more flexible and potentially more cost-effective. However, challenges remain. The need to decarbonize electricity generation to combat climate change is urgent. Integrating large amounts of intermittent renewable energy into the grid presents technical challenges. Ensuring access to electricity in developing countries while meeting global climate goals is a complex issue. The electrification of transport and heating, crucial for reducing overall carbon emissions, will place increasing demands on electricity grids. This will require significant infrastructure upgrades and smart management systems. Cybersecurity is another growing concern. As power systems become more interconnected and reliant on digital technology, they also become more vulnerable to cyber attacks. Protecting critical electricity infrastructure is becoming a major focus for governments and utilities around the world. From Thales' amber to Tesla's coils, from Franklin's kite to modern solar farms, electricity has come a long way. It has lit up our world, connected us across vast distances, and powered a technological revolution beyond the wildest dreams of those ancient philosophers who first noticed its effects. Throughout this journey, we've seen how theoretical discoveries led to practical applications that changed the world. From Faraday's experiments to the global power grid, from Volta's battery to today's smartphones, electricity has been at the heart of technological and social progress. We've also seen how our relationship with electricity has evolved. Once a mysterious force, it's now so ubiquitous that we often take it for granted. Yet as we face the challenges of the future, climate change, growing energy demands and the need for reliable, clean power, electricity will undoubtedly play a crucial role. The story of electricity is far from over. As we stand on the brink of new breakthroughs in power generation, storage and distribution, we're reminded that the most exciting chapters may be yet to come. The next great electrical revolution could be just around the corner. The challenge of providing clean, reliable electricity to a growing global population while combating climate change will be one of the defining issues of the 21st century. How we meet this challenge will shape not just the future of electricity, but the future of our planet. As individuals, we all have a role to play in this ongoing story. From the choices we make as consumers to the policies we support as citizens, we can influence the direction of electricity's future. Whether it's adopting energy-efficient practices, supporting renewable energy initiatives, or staying informed about emerging technologies, we can all contribute to shaping a sustainable electrical future. Thank you for joining us on this journey through the electrifying history of electricity. If you enjoyed this video, don't forget to like and subscribe, and let us know in the comments what electrical invention do you think has had the biggest impact on society? Or what future electrical technology are you most excited about? Remember, every time you flip a switch, charge your phone, or boot up your computer, you're participating in the ongoing story of one of humanity's greatest discoveries. The future of electricity is in our hands. Stay curious, stay energized, and until next time, keep the current flowing.